Okay, just look at this bridge. The film is real. It is not moving because of an earthquake, and the video is not sped up. Yeah, the road really moved like this. That morning, the wind was strong, but it was not a hurricane. Still, the road moved like a giant ribbon. In a few minutes, a huge part of the bridge would break off. It would turn over and fall into the water. The bridge was only 4 months old. 4 months! That's it. But here's the really strange part. People knew it moved before it even opened. Some workers became sick from the movement. They gave the bridge a nickname, Galloping Gertie. Engineers tried to fix it. Yeah, they added large shock absorbers, they tied parts of the bridge down with steel cables, they even built a small copy and, tested it with wind. During one test, an engineer saw the road twist. He knew that if the real bridge ever twisted like that, it would just fall. So, why did the bridge stay open? And how could a normal wind actually tear it apart? This is Failure Atlas, and this is the story of the Tacoma Narrows Bridge. The Tacoma Narrows is a stretch of water in Washington state. Tacoma is on one side and the Kitsap Peninsula is on the other. Back then, people had to cross the water by ferry. A bridge would make the journey much faster. Sounds simple, right? Well, the bridge had to be very long. The middle part would hang above more than half a mile of open water. There could be no support under it, so the road had to hang from two huge steel cables. This is called a suspension bridge. It would become the third longest, bridge of this kind in the world. So an engineer named Clark Eldridge made the first plan. Clark wanted a strong steel frame under the road. Think of the frame like the bones of the bridge. It would be 25 feet tall. That is about as tall as a two-story house, actually. The frame would make the bridge heavy and hard to bend. Strong, solid, yeah, pretty safe, you would think. But it would also cost a lot of money. The price was around $11 million. But the project needed help from the US government. The government agreed to help, but it wanted a cheaper bridge. So it brought in a famous engineer from New York. His name was Leon Moiseev. And to be fair, Leon wasn't some careless beginner. He was one of America's most respected bridge engineers. Leon looked at Clark's heavy frame and thought it wasn't needed. So he removed most of it. Instead, he put two solid steel walls along the road. These walls were only 8 feet tall. That saved steel and, of course, a lot of money. And it made the bridge look thin and beautiful, but it also made the road much easier to bend and twist. And yeah, that would become a very big problem. The final bridge cost about $6.4 million. It took only 19 months to build. And on July 1st, 1940, the bridge opened. There was just one tiny problem. It had already started moving. Not after a few years, but before it even opened. Can you imagine? Workers first felt the movement while building the road. When the wind blew, a wave moved along the bridge. One part of the road went up, another part went down. Then they changed places. Some workers actually became seasick. Drivers felt it too. A car ahead could disappear behind a wave in the road. Then a moment later, it would appear again. Just imagine driving across that. People even came to watch. And that's why they actually called the bridge Galloping Gertie. It was funny to watch, sure, but the engineers were worried a lot. First, they added 4 large shock absorbers near the towers, and they did almost nothing. Then they used strong cables to hold the road down. This helped near the ends of the bridge, yeah, but it did not stop the middle from moving. One of those cables later broke in strong wind. So yeah, the state needed a better answer. So it called Professor Bert Farquharson. Bert and his students built small models of the bridge. They placed them inside a wind tunnel. A wind tunnel is basically a large tube with a powerful fan. It lets engineers see what wind does to a building or a bridge. And this is where the story gets a little scary. During a test, Bert saw the little road twist from side to side. This was different from the normal up and down wave. He knew this new movement could destroy the bridge. And soon he would see it again. Not on the model, but on the real thing. By early November, Bert's team had found the main problem. Remember those solid steel walls beside the road? Wind could not pass through them. Well, those walls caught the wind almost like a sail. You can probably see the problem already, right? Bert suggested two ways to fix this. They could cut openings into the walls. Then the air could pass through. Or they could add curtain covers. These would guide the wind safely around the road. So on November 6, the engineers finally agreed on a plan. The next morning, Clark started making drawings. The first covers could be added in 10 days. The whole bridge could be protected in 45 days. Sounds good, right? Except the bridge didn't have 45 days. It didn't even have one. The very next morning, on November 7th, wind blew across the water. It hit the solid side of the bridge. The wind reached about 42 miles per hour. That's strong wind, sure, but again, it's not a hurricane. The road began its usual up and down wave. Bert arrived with a camera. He wanted to study the movement. At first, he saw nothing new, just the usual wave everyone already knew. Then, shortly after 10 o'clock, everything changed. The road stopped moving like a wave. It started twisting, and not just a little. One side rose high into the air, and the other side dropped. Then they changed places. The road tilted as far as 45 degrees. It made this huge movement again and again. This was it. The movement Bert had seen in the small model. The movement he believed would destroy the bridge. And now there was no way to stop it. A newspaper editor named Leonard Coatsworth had just driven onto the bridge. His daughter's dog, Tubby, was in the back of the car. The moving road threw the car against the side. Just imagine being inside that car for a second. Leonard climbed out through a window. He couldn't even stand on the twisting road, so he crawled toward the tower. Then he slowly made his way back to safety. Officials immediately closed the bridge. Several people tried to save Tubby. Bert tried too, but Tubby was terrified and bit his hand. The road moved too violently. Everyone had to turn back. Honestly, they had no other choice. At 11 o'clock, the bridge started breaking. Concrete fell into the water. Steel cables snapped like gunshots. Large beams bent and twisted. At 11:02, a piece of road broke free. It was almost as long as 2 football fields. It turned over and fell into the water below. More parts followed. By 11:10, the middle of the bridge was all gone. Somehow, no people died, but sadly, Tubby was still inside the car and didn't survive. Okay, so what actually happened here? You might have heard that the bridge fell because of resonance. That answer is not completely wrong, but it misses the most important part. The main problem was something called torsional flutter. It sounds complicated, I know, but honestly, the idea is much easier. You know when you put your hand outside of a moving car? Hold it flat and the air flows around it. Now, turn your hand just a little. You can feel the air push your hand up or down. Well, the bridge worked in a similar way. A small twist changed how the air moved around the road. The air pushed the road and made the twist larger. When the road twisted back, the air helped it again. The wind was basically feeding the movement. One twist helped make the next twist, and every new twist became bigger. A good bridge should slowly calm down after it moves. This one didn't. It was long, thin, light and easy to twist. Its solid sides caught the wind. The bridge took more and more energy from the air. Finally, the steel and concrete just couldn't take it anymore. The bridge just tore itself apart. Now, it would be easy to blame one engineer, but honestly, one person didn't cause this. It was a whole chain of choices. The stronger plan cost too much. The cheaper plan followed the best ideas of that time. Those ideas focused on the weight of cars and the bridge itself. Wind seemed less important. The bridge moved before it even opened. But after a while, people treated the movement like a strange feature, almost like it was just part of the bridge personality. The first repairs tried to stop the movement. They did not remove its true cause. The wind tests found the real danger, but the tests came late. And the final answer was still on paper when the wind arrived. And there is one more part to this story. Older bridges had already been damaged by wind. Engineers once made bridges heavy and stiff because of this. But many years passed. The old warnings was slowly forgotten, so the danger wasn't completely new. People had simply stopped looking for it, and that's a pretty uncomfortable thought. After the collapse, investigators didn't blame one person. They said bridge engineers everywhere needed to understand wind better. New suspension bridges became harder to twist. They were also shaped so wind could move through around them. Testing bridge models with wind became normal. In 1950, a new bridge opened in the same place. This bridge had a deep, open frame below the road. Air could pass through it, and the frame made the road harder to twist. And that bridge is still standing today. So, in the end, the Tacoma Narrows Bridge was strong enough to carry cars. Yeah, but that wasn't enough. The bridge also had to live with the wind. The bridge, the air, and the movement became one system. And somehow, that system turned against itself. And that, I think, is the real lesson. Something can look safe in every normal test, but the real world might ask a question nobody tested. Sometimes the greatest danger is not a force you cannot see, it's the one you decided wasn't important. If you enjoy simple stories about complicated failures, well, consider subscribing to Failure Atlas and tell me in the comments what failures should we investigate next.